Hello, my name is Nolan Gregory, and this is my final project. So I'm away from my main computer right now, and I don't have Maven set up on this one, or I should say I don't have the path set up properly on this computer. So I'm just going to build this project through IntelliJ. The process would be exactly the same if I were building it through Maven. I would just do it through the command line. So I will build and run this, and we can take a look at sort of the UI here. So what pops up is this window that is custom made by myself, which is why it looks so bad, because I'm not a UI designer. Up top, we have 3 buttons that sort of act as the navigation system for the app. We have a custom close button over here, and that's because I sort of bypassed Java effects built-in minimize, resize, and close buttons because I like the way that this looks more. We have a little kiwi bird logo here because I think that that's cute. We have 2 buttons, load image and save image. We can see here that save image is sort of grayed out. I can't click it because if I were to try to save an image that doesn't exist, you can imagine the problems that would have. I'd most likely get like a null pointer exception if I tried to do that. Over here, we have our filters and effects. So the top 4 are kernel filters. So they go through a kernel algorithm, which I'll explain, or sort of a manipulation algorithm, I should say. Laplacian is an edge detection algorithm, and we'll talk about that when we get there. Gaussian, I'm using in this instance as a blurring algorithm. Sobel is another edge detection, and then sharpen is a really basic elementary kernel that we can use to sharpen the image. And then we have 4 effects down here, so real basic ones: grayscale, invert, saturate, and then modify the contrast of the image. So I'll go ahead and load an image real fast. So I've got a couple images preloaded here. We'll just open this one. So this is a histological slide. You could call it a histopathological slide or pathological slide. It's essentially just a slide that a pathologist will use to determine whether an individual has some sort of disease, right? It's used in the diagnosis of diseases. Some of those diseases could be things like non-Hodgkin's lymphoma and, what's another one? Acute myeloid leukemia, that could be one. Essentially, they'll look at this and they'll look for distinctive patterns or cell structures that are anomalous. And one thing that you might know of already is that machine learning and convolutional neural networks are really at the forefront of this sort of field right now because people are using them to sort of detect these anomalous features in these slides themselves. But before that, right, there were just basic edge detection algorithms. And that's what I have here. I don't have a convolutional neural network, right? I can't just build that myself. So we'll throw a Laplacian edge detection down, and we see that this is doing a really good job at detecting the edges relative to what we just saw. So if I go back here, we can see that this, these edges aren't really that defined, but whenever we put the Laplacian detection down, we can really see those edges really well. So that's where this algorithm kind of excels. We'll do Sobel, which is another edge detection. You can see it's a little bit worse, and I'll talk about that in a second. And then lastly, we can sharpen this image up. So we'll look at this relative to the grayscale. Okay, kind of hard to see things, but we sharpen it. Now some of these features are really sharp and really recognizable. So we'll load another image in here. We'll load this picture here of a Coke can. And looking at this, we can see that this is probably going to excel when it comes to this these edge detection algorithms. Why is that? Because we have these really sharp defined edges here on this pattern here, this font, and the edges of the can itself. So if we put a Laplacian filter down, we can see that it looks really good. And that's because, again, this filter excels, or this, I suppose filter is a fine word. It excels whenever you have these really sharp defined edges. If I put Sobel down, it's a little bit worse, and again, I'll talk about that. If I sharpen it, we can see that it looks pretty sharp in comparison to the just regular grayscale. So those two side by side, pretty obvious. We can invert it, right? So this just takes all the colors and inverts it, pretty obvious. And then we can saturate it. So the saturate just makes it a little bit more colorful. It pops, makes the red really pop. And then high contrast, we should really call it low contrast because I changed it halfway through. And I suppose we can talk about these filters real fast. So Laplacian, as I said, is an edge detection algorithm, and all of these sort of kernel algorithms, you can see how slow it is. It runs at O of n squared times m squared time complexity. So n squared being the dimensions of the image itself. We're just, for simplicity's sake, assuming that it is a square image where the height and the width are the same, and m squared is the size of the kernel, right? So this kernel on the Laplacian filter is, oh man, it's a 9 by 9 kernel, right? So that's 9 squared. So my m is 9. So we have n, when this image is 1400 by 1400, it's a square image. So 1400 by 1400. So 1400 squared times, and then 9 squared. So you can see that this takes a really long time because every single pixel here, right? We look at this first pixel, well, it has to go through 81 iterations, right? 9 squared iterations, essentially, because it's a double for loop. And then the next pixel has to go through that. Then the next pixel. And it has to happen 1,400 times squared, right? So there's a lot of a lot of operations that occur in this image. So Bell is a little bit different because it's technically 2 times n squared. Oh, sorry, 2 times n. Oh, geez, what is this? N squared times 2 times m squared. But you know, with big O, you drop the coefficients and the constants. So we just have n squared times m squared again. But the size of the matrix itself is a lot smaller. So this is a 3 by 3 matrix as opposed to a 9 by 9 matrix. Sharpen runs really fast because, again, that's just a 3 by 3 matrix. And then these ones run almost instantaneously because it's just n squared time complexity. You have to loop through every pixel, essentially. And that's pretty much it. Really fun project to work on. I really learned a lot about sort of the JavaFX UI design. Not really great at UI design. You can tell by how bad these buttons look, but hopefully it was a interesting project to sort of look into and listen to. So thank you, and I hope you liked it. Anyway, have a great summer. I will see you next semester. Thank you, and goodbye.